today itself. Yesterday's work also will be shared within a 3, 4 to 5 days time. But today we are going to solve a numerical, and that you will be able to have it at your dinner time. Why? Because today when I show you, we discuss, you will be asking me some questions. Based on that, I'll be adding some material to it. That is the reason I am not sharing it today, but it will be always shared. Okay, so we are 31 now, and is sufficient enough to begin with the class. So here I am. So friends, let us begin with a small discussion. Every engineer has to deal with the machines and the structures. Well, structures like residential buildings, schools, colleges, libraries, hospitals, shopping malls, stadiums, those structures are with everybody, but some special structures, say for example, aircraft. If you see the aircraft in a detail, then its approximate shape like this is made up of a lot of circular sections. I can show many a jazzy picture, but that is not required. And then there is a platform over here. On the top, there are passengers here, and here there is a normally a baggage area, and maybe some machines are also kept. Same is a part of a wing. It has a fuel tank also. Now, what is most interesting is that these structures are subjected to the variety of the force, and those without those force, it's simply they are meaningless. For example, there is a lift given to it, then it is a weight, then there is a thrust, there is a resistance, there is a cargo. Under the influence of it, it is supposed to function. So it should have a strength. Strength is a something which opposes the deformation. Now, which opposes the deformation when something tends to deform when the forces are acting upon it. If forces are acting upon it, then we should have a exact and a great knowledge of a forces so that we know what is the result of that force on that particular structure. This is a job of a mechanics and a solid mechanics. Now, ships are even much larger and much more complicated. Excuse me, complicated structures. There are members going in a longitudinal direction like this. Then there are those bulkheads, partitions. Then there are different legs. There are beams inside, columns inside, etc. Now, we have to understand one particular thing. Complex structures are made up of some simple instruments, simple things, structural elements like beams, columns, plates, etc. Beam is a long, slender, prismatic object which can be supported in a variety of the way and it is loaded. This is the axis of a beam and the load is perpendicular. But sometimes slender objects are kept vertical, may be fixed at a one end or a both end. Again, this fixing can be in a variety of the way. Both end hinged, etc. Such things are called columns or there is another name also strut. These and then there are plates, maybe straight and flat or which are given a particular shape. These things are assembled in a variety of the ways and structures are made. Simple most structures are, the frame. Maybe a frame is having a hinge support also over here. And here it is fixed. Right? These are the frames which can be loaded. Then there can be frames which are three-dimensional. And there are trusses. What are the trusses? In a steel structure building, roofs are having this kind of a structure. It can have, say, a variety of it. There can be a trusses like There can be many other varieties. These trusses are always made with a different kind of a triangles. Watch. Here also is a triangle. This also is a triangle. This also is a triangle. This also is a triangle. Different shape. But triangles are a basic element. And in trusses, every joint is a pin joint. Which permits a rotation. Now, at every pin joint, all the members meet in a one particular point over here. There cannot be a truss. See, if we have something like this, then this is not a truss because there is a square element over here. Yeah, if I connect it like this is a truss. Okay, same way, if there is a girder like this, then this is a truss. But if it is straight, there are rectangles only, or not all the rectangles are, these are open rectangles, then this cannot be treated as a truss. Also, if this is not a truss, because here we have a rectangle. And here also we have a rectangle. Now let us enjoy a one small video, and then let us come back to one numerical that we will solve today itself. Sorry for this ad, but you have to listen to this ad for 4 seconds.
Ok, donc, dans le fond,
They are used in bridges, antenna towers. Trusses are everywhere. They are used in bridges, antenna towers, cranes.
Just mark that there are triangles everywhere.
Antenna towers, cranes.
Look, here we have a triangles. Maybe triangles are in the 3D, but there are triangles.
Even in parts of the International Space Station. And for good reason. They allow us to create strong structures while using materials in a very efficient and cost-effective way.
This is a main advantage of a truss. It can give us a maximum strength with a minimum of a material or a mass or a weight. No other structural arrangement, if you make something solid from the plates and the rods and the bars, it will be heavy. Sometimes those kind of elements also required, but truss is a champion of a material saving. Remember that.
So what exactly is a truss? It is essentially a rigid structure made up of a collection of straight members.
Remember the word straight over here. All the members are straight. There are no curved members in a truss as such. Sometimes there are, but most of them are straight.
But that's not a complete definition. There are two important assumptions we need to be able to make for a structure to be considered as a truss. First, we need to be able to assume that all of the joints in the structure can be represented by a pinned connection, meaning that members are free to rotate at the joints. The members of a truss are often rigidly connected using what is known as a gusset plate.
Look, here there is no pin. You cannot see a pin over here, but all these central lines are meeting in a one point. In that case, it is as good as having a pin. It will behave like that only. It will permit a rotation. This assumption must be very, very clear.
But if the center lines of all the members at a joint intersect at the same point, like they do here, it's reasonable to assume that the joint behaves like a pinned connection. The second assumption we need to be able to make is that loads are only ever applied at the joints of the truss. We never have loads acting in the middle of a member, for example. Because all joints are pinned, the members cannot carry bending moments. They can only carry axial loads. This simplifies the analysis of a truss significantly. Each member has to be in equilibrium, so the forces acting at each end of a member must be equal and opposite. Each member is either in tension or in compression.
What does this mean? Here, first of all, suppose we talk about a truss like this. Then loads are acting at the joints only. Say maybe here there is some force, here also there is some force, and here is a joint where it is supported, there also support reaction will come. Truss analysis, when there is a force in between, then it doesn't behave with the only tension and a compression, it changes altogether. For example, when this truss is subjected to a load, every element will come in either a tension or a compression. finding out all the members' tension and compression when it is loaded with some specific load. That is called a truss analysis, and that is what we are going to learn in detail in this semester.
These assumptions are what differentiate a truss from a frame. Unlike trusses, frames don't necessarily have pin joints, and so members can carry bending moments. A frame can also have loads applied.
Frame has a welded joint. This part cannot rotate with respect to this one. And here load may be applied to the middle of a member, but that is not the case with the trusses.
applied directly to its members. The base shape of a truss is 3 members connected to form a triangle. If a load is applied, the angles of the triangle won't be able to change if the length of each of the members stays the same. This means that the triangle is a very stable shape which won't deform when loads are applied to it, and so it is a great base from which to build a larger structure. Joining 4 members together does not form a stable structure. The angles between members can change without any change in the length of the members, and so using a 4-sided shape as the base for building a truss would be a terrible choice. An easy way to stabilize this configuration is to add a diagonal bracing member to split it into triangles. We can start with our triangle and build it out to form a structure. There are a lot of different ways to build a truss, but there are some particularly popular truss designs that you will see again and again, and so they are referred to by specific names. The one shown here is a Fink roof truss, but there are many more, as you can see here. Later on in this video, I'll cover how these different designs carry loads in different ways. The members of these trusses are all located in the same plane. These are called planar trusses, and we can analyze them as 2-dimensional structures. Even seemingly 3-dimensional structures can often be analyzed as planar trusses. Take a look at this bridge, for example. The loads are transmitted from the horizontal floor beams to the 2 vertical trusses on each side of the bridge. Each of these trusses only carries loads acting in its plane, and so we can analyze it as a 2-dimensional structure. To be able to design or analyze a truss, we need to be able to determine the force in each of its members. This allows us to check that the member can carry the loads without failing, or gives us the information we need to select the best cross-section for each of the members. There are 2 main methods we can use to do this, the method of joints and the method of sections. Let's look at the method of joints first, using the Fink roof truss we saw earlier. The method is really simple. First, you draw a free body diagram, showing all of the
Note that here we have a roller joint.
external loads acting on the truss. Using the Fink roof truss we saw earlier. The method is really simple. First,
This is a roller joint, whereas this is a hinged joint. Roller joint is a movable hinge, and this is a fixed hinge. So this one can give a upward load reaction and the horizontal also. In this case, it can be only upward. Now a problem will be solved in front of you, but we will solve a problem in our own way.
First, you draw a free body diagram, showing all of the external loads acting on the truss. and you use the three equilibrium equations to calculate the reaction forces.
You can see, as the free body diagram is drawn over here, we removed the support, but forces which are given by support are there as it is. Here, this force has come as a reaction support, but support is not shown. We are interested in the truss, so we have taken an entire truss and we are showing all the forces acting upon it externally. Actually, there are tensions and a compression maybe inside these elements also, but they are all internal, so they are not shown in a free body diagram. If anybody has any curiosity or any confusion, we can discuss it further, or else we'll go ahead with our video.
Then you draw a free body diagram for every single joint and work through them one by one to solve the unknown forces acting at each joint. You solve the unknown forces using the equilibrium equations. Since all of the joints are pinned connections, there are no moments, and so you only need to consider equilibrium of the horizontal and vertical forces. Remember that we are calculating the forces acting at each joint, not the forces in the member. If a member is in tension, the internal forces will be acting to make the member longer. For every action, there is an equal and opposite reaction, which means that a member in tension will be exerting a force on the joint which is acting away from the joint. For members in compression, the force will be acting towards the joint.
This is a very important point to understand. Suppose this is one joint on a truss, this is a second joint on the truss, and a member between it is in compression. That is, this member is being compressed by the external agency. So what does it do? It is trying to oppose it. So it gives a radially inward force to the joint. This yellow one. Okay. Same way, if this part is in tension, external agencies are pulling it. As a result, it is trying to pull back them. So it is pulling that, it is giving a radially outward force on the joint. Dear friends, do not resist yourself. If you want to ask a question, do ask.
Let's work through an example for a slightly.
For example, over here, you can see that this element, all elements are shown in a tension over here. What I mean to say is, this particular part is being pulled. It is being pulled outside. As a result, it is pulling the joint towards it. This is pulling the joint towards it. Okay, so this is in tension, so it is giving a radially outward force on the joint. This is in tension, so it is giving a radially outward force on the joint. Well, you can assume it to be in a compression also. Now here, if you assume every part to be in tension, and when you find out this tension is negative, then we know that it is actually in a compression.
Simpler truss. First, let's draw the free body diagram and determine the reaction forces using our three equilibrium equations. Taking equilibrium of the horizontal forces, the horizontal force at joint A must be equal to 0, because it is the only force in the horizontal direction. Taking equilibrium of the vertical forces, the reaction forces at joints A and E must sum up to 20 kilonewtons. Both joints are located at the same distance from joint C, so taking equilibrium of the moments acting about joint C, we can calculate that they both equal 10 kilonewtons. Now let's determine the forces acting on each joint. Since we don't know yet which members are in tension and which are in compression, it's easiest to just assume that all of the members are in tension, and so we'll draw the internal forces as pointing away from each joint. If we end up with negative values for these forces, it just means that we guessed wrong, and the member is actually in compression. Now we can work through each of the joints, starting with joint A. Analyzing trusses involves a lot of resolving forces to different angles. So if you want to be good at it, you're going to need to remember your trigonometry. Here's a
Okay, dear friends, here this is a support reaction we have found out. Then we have assumed that this truss element is in a tension, so this joint is pulled outward by a force AB. AB is a member and a AC. It is being pulled outside. Now, this joint is in equilibrium, it is not getting accelerated, so sum of all these three forces has to be 0. Okay, so if you do that, then what result we get? Just see.
quick reminder. Back to our joint. All we have to do is apply the equilibrium equations to determine the unknown forces at joint A. Taking equilibrium of the vertical forces, the 10 kilonewton reaction force must balance the vertical component of the force FAB. And so we can calculate FAB as negative 10 divided by sine of the angle of 60 degrees. Taking equilibrium of the horizontal forces, we get that the force FAC must balance the horizontal component of the force, FAB, and so is equal to 5.8 kilonewtons. That's all of the forces acting on joint A calculated. The force in each member is constant, and so we now also know the forces acting on the joints at the other ends of these two members. We can repeat the process for joint B. We can start by considering equilibrium of the vertical forces, which allows us to calculate the force FBC. And then we can consider equilibrium of the horizontal forces to calculate FBD. We then need to work through all of the remaining joints, but we can save a bit of time by noticing that the truss and the applied loads have an axis of symmetry, and so the forces on the other side of the truss must be identical. That gives us all of the forces at the joints. We can show which members are in tension and which are in compression, like this. One thing you'll notice as you analyze trusses is that some members don't carry any loads at all. We call these zero force members. There are two main configurations where we have zero force members. The first is where we have three members connected at a single joint, and two of the members are aligned. Here, only one member has a component in the vertical direction, and so to maintain equilibrium of forces at the joint in the vertical direction, the force in this member must be 0. The second configuration is when we have only two members connected at a joint, and the members are not aligned. Only one member has a component in the vertical direction, and so both must be zero force members. By the way, this is true regardless of how the members are oriented, because we can rotate the orientation of the coordinate system we are using to apply the equilibrium equations. These two configurations only contain zero force members if there are no external loads acting at the joints. If we have external loads, there will be components in the vertical direction, and so these will not be zero force members. Let's look at an example. At this joint here, we have two connected members. The members are not collinear, and there are no external loads, so they must be zero force members. And at this joint, we have three members, of which two are collinear. The vertical member must be a zero force member. We can remove these members, and so have a much easier starting point for solving the truss. You'll notice that we haven't removed the two members at this joint. That is because there is an external load acting here, and so these can't be zero force members. You might be wondering why anyone would bother including zero force members in a truss if they carry no loads. They are definitely not useless. They are usually included to provide stability, for example, to prevent buckling of long members which are under compression. Or they may be used to make sure that unexpected loads won't cause the structure to fail.
According to Mr. Warren Buffett, in the stock markets, when the tide is up,
We've covered the method of joints. Let's look at the other method we can use to solve trusses, which is the method of sections.
Before we study the method of sections, let us solve one of our numerical in a method of joints. Please pay attention. It will not take a lot of time. It is very interesting. Dear friend, this is a problem made by me. This problem will be sent to all of you in the group today itself at the end of the day. Kindly have a look at this. Here, this is a given truss. You can jolly well see it. This truss is supported here and here. And these are the forces acting upon it. Please note that every force is acting upon a joint. Am I right?
Yes, sir. Yes, sir.
So this joint, this joint, this joint, this joint, and this joint are all subjected to a load. All loads are 8 kilonewton. Okay. Now, dear friends, remain very, very frank. You can stop me anytime. There will be a support reaction over here and here. I am showing it to be a 40 kilonewton and a 40 kilonewton because I have already calculated it. Do you agree that it is 40 kilonewton? What is the total load? 8 plus 8 plus 8 plus 8 plus 8 by the 40 plus another this 40 kilonewton. So total load is a 80 kilonewton. There is a perfect symmetry everywhere. As a result, 40 will go here and a 40 will go over here. Or you can do that stunt. You can say this is a reaction R1, this is a reaction R2. R1 plus R2 will be equal to how much? 40 plus 40, 80, excuse me. Okay, then take a moment about this point. If you take a moment about that particular point over here, then moment of a R1 will be 0, R2 will not be. So you can say 80 into this much plus this 8 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 into this whole length up to this much plus 8 into this much, all these forces, and then minus R2 into total length, because moment of a R2 is in a opposite direction than the moment of a all 8. If you do it, R2 will come out to be 40. Have I made myself clear, my dear friends? If not, see, sometime it may so happen that I might be explaining you something very, very simple and you might get bored. But there may be someone in our division who may be wanting to understand it, so I cannot bypass that. Right? Today you can say our actual learning begins. We are entering the subject. Now, having done this, I come to the joint A. This is a A and this is a H. So this is a AH element. This is a A and this is a B. So this is a AB element. Now, first and foremost thing, this is a theta, this is theta, this is theta, this is also theta, this is also theta, this is also theta. Okay, same way this is theta, this is theta. Correct? And all remaining angles you can call phi. This is phi, this is phi, this is phi, this is phi. Now you may be given this height and you may be given this length. As a result, you can find out tan theta and hence theta. You can find out tan phi and you can find out phi also. Okay. So what I have done at the point A. Now I want you to understand that this is a point A and the support reaction is acting upward. Here there is a element AB and here there is a element AH and here there is an angle theta. Now sum of the vertical forces is 0. So force by AH, vertical component will be here. And this one does not have a vertical component at all. So sum of this and this has to be 0. So this must be directed in a downward direction. So FAH should be acting like this. Am I right, my dear friends? Have you understood how I have guessed it? It is simple. I don't want to insult your intelligence, but sometimes, a confusion may remain. The way I look at the things and you look at the things may be different, or you may have something easier to achieve this. So you please talk to me directly. Anybody wanting to comment further? Why I am taking AH downward? Okay. Now one more thing. AH is downward, so it will give a component in this direction, horizontal component. So FAB has to be like this. Am I right? So now this is a joint A, this is a support reaction, and this is a force because of a AH, and this is a force because of a element AB. Now FAH sin theta is like this, which is equal to 40. So FAH is a 40 by sin theta. What is sin theta? I do not know now, but it is so. Well, when you solve a problem in the exam or in a textbook, angle will be given to you, but I am solving a general problem. And FAH cos theta should be equal to FAB in the magnitude. So FAB is equal to FAH is a 40 by sin theta. So 40 by sin theta into cosine theta is equal to 40 by tan theta. And I can conclude that AB is in tension and AH is in compression.
Excuse me, sir.
Yes.
Sir, please repeat it again.
Whole thing? Okay, I will do that. Thank you very much. Have you understood, cadet, that here is a support reaction of a 40 kilonewton?
Yes, sir.
Okay. Then there is a some force in this direction by a member AH. Okay. We don't know whether it is like this or like this, but it is AH and there is another force in the direction AB. Cadet, is this clear to you?
Yes, sir.
Okay. Now this point is in equilibrium. Sum of all the forces acting upon it is 0. So all the sum of the vertical component is 0 and the sum of the horizontal component is 0. Am I right?
Yes, sir.
Okay. Now this support reaction is upward only. This does not have a vertical component. FAH has a vertical component over here. Now vertical component of a FAH plus this 40, their sum should be equal to 0.
Yes, sir.
So this has to a direction like this. Do you agree with me?
Yes, sir.
Okay. If vertical component of FAH is downward, then FAH must be in this direction.
Yes, sir.
Okay, good. Now FAH will be having a horizontal component like this. That horizontal component should be equal and opposite to the FAB. Then only horizontal component should be equal to 0.
Yes, sir.
FAH is pushing this point in this direction. So FAB should pull it back, isn't it? This
Yes,
is
sir.
how I am writing it now. Have a close look at this and you will know what I have said. FAH sine theta is this force because this is theta. FAH sine theta is equal to 4t. So FAH is equal to 4t by sine theta. FAH cos theta is equal to FAB. FAH cos theta will be in this direction. That should be equal to FAB. So FAB is equal to FAH is a 40 by sine theta into cos theta, which is equal to 40 by tan theta. Now, remember, here FAH is pushing this point like this. AB is pulling this point like this. Now, we just now saw in a video, or let me repeat it over here. If AB is pulling this point in this direction, then that point is pulling AB in the opposite direction. So this point of point A is pulled outward. So B also must be pulling it outward. So AB will be in a tension. Am I right? Have you understood this?
Yes, sir.
Anybody else would like to have a dialogue with me? Most welcome. That is in the tension, so I am writing a T over here. Now, same way, element AH is pushing the point A in this direction. So, this point is pushing AH in this direction. So, point A is being pushed in this way. So, H also must be pushing it this way. So, AH is in compression. That's why we write as C over here. Okay. At this point, we were knowing only one force. Now, with the equilibrium, we found out a force in a AH and a AB both. Now is the time to go to a node H or a node B. I would like to ask everybody again, have you understood how we have found out forces in a AH and a AB? Cadet Patidar, have you understood today?
Yes, sir.
Yes.
Jatin, how about you?
Yes.
Okay.
Fine.
Yeah, now we'll go to another joint, but that will be possible in the next class. This PPT will reach you before end of the day. If I make changes, then that change version also will be sent to you again. So now, dear friends, and once it is all the changes have taken place, after I've discussed with division 2, 4 and 6, final version will come to the Moodle. So be patient. Every class material will be sent to you more or less on the same day, but Moodle entry may take a little time. So that it is in such a way on the Moodle that everybody's questions are answered. Now it's 3 o'clock. You should be free to take a, what do you call, a
Good afternoon to all of you.
Good afternoon,
Good
sir.
afternoon, sir.
Good afternoon, sir.
Am I audible?